Buongiorno a tutti. Good morning, good afternoon, good evening. Hello, everyone, wherever you might be. Today is my great pleasure to introduce Alessandro CAROTENUTO, who is from Prague, actually, now. He's going to tell us about the Borel-Weil theorem for reducible quantum flag manifolds. Alessandro, the Zoom is yours. Take it away.
Thank you, Piotr, and thank you for the introduction and the presentation. And I wish to thank everybody for being here, of course. So the work I'm going to talk today is a joint work with Freddy Diaz-Garcia and Raymond Obohala. Both of them are working here together with me in Prague. And so let's begin. This is a table of content of the work, of the talk. I will start with a gentle, brief introduction, which is both historical and conceptual introduction to the Borel-Weil theorem. Then I will also talk about some material which I presume is well known to most of the crowd, but nevertheless should be discussed. So I will discuss about Drinfeld-Jimbo quantum groups, then differential calculi, and we will go to the specifics of quantum flag manifolds. Then we will talk about the holomorphic structure and the line bundles, and all of this is just to introduce all the machinery that we need to talk about the Borel-Weil theorem in this context. Then, time permitting, I will say something about quantum principal bundles and the recent definition of principal pairs, which is an object that together with Raymond and Colin Morozinski we defined to give a characterization, to give a presentation of quantum principal bundles in some specific context. And then we will review the Borel-Weil theorem for non-commutative quantum flag, for quantum flag manifolds, irreducible quantum flag manifolds, sorry. So let's start with the classics. Borel-Weil theorem is a pivotal theorem in geometry, in particular in that branch of geometry which is known as geometric representation theory. That is not other than the school of thought that if we think of a Lie group as a geometric object, then we should be able to realize, as we are, all the representation theory with some geometric construction, involving in particular the differential structure of the Lie group. This theorem was for the first time reported by, it was attributed to Borel and Weil and reported for the first time by not other than Serre during the Bourbaki seminar, the 100th Bourbaki seminar to be precise. So it realizes, this theorem allows us to realize each representation of a complex semi-simple Lie algebra as the space of holomorphic section of a line bundle over a flag manifold, which is not other than an homogeneous space for the Lie group corresponding to the Lie algebra. So it would be very difficult to overstate the importance of this theorem, not just for the nice conceptual framework that I just described, but also for the theorem that were proved as a consequence of the Borel-Weil theorem through the years. I quite arbitrarily choose to make a list of three other consequences, which were the Borel-Weil bot theorem, or bot Borel-Weil, or any possible combination of these three names, which is a generalization of Borel-Weil to higher cohomologies. Then another surprising consequence of Borel theorem is Kummer's decomposition of the tensor product of two irreducible finite dimensional representation of a complex simple group. And for me, it's quite surprising that such a representation theoretic question requires the knowledge of the geometry of the two corresponding homogeneous spaces and requires also that we know about Borel-Weil. And let me just mention finally the Bernstein localization theorem in algebraic geometry, which is a far-reaching application of the Borel-Weil theorem in the context of algebraic geometry. So it's not a surprise then that since the discovery of quantum groups that we consider as we should the correct non-commutative generalization of Lie groups, we have seen a lot of non-commutative generalizations of this theorem. Let me mention some. First of all, there were some purely algebraic approach, like the derived functor approach of Anderson, Paul, and Venn. Then the quantum coordinate algebra approaches of Paschal, Wang, and Mimachi, and Nomi and Yamada. From a more mathematical physics point of view, the approaches of Bindran and Low based on Q boson also allowed to prove the Borel-Weil theorem. And here in Prague, Juszczak and Stovicek proved the generalization of the Borel-Weil theorem through the use of coherent states. In the sister algebraic context, Gover and Zhang proved the Borel-Weil theorem as well. And finally, let me again refer to the Bernstein localization theorem that was generalized in a non-commutative context by Kremnitzer and Beckley. Now, all these approaches didn't introduce any notion of holomorphicity. They all took advantage of the fact that in the classical case, and it's expected the same also in the quantum case, the holomorphic sections of a Lamb bundle over a flag manifold are the same as the Borel invariant sections. So here, what they were generalized was the Borel invariant description. And so far, there is no proof there was no proof in a non-commutative differential framework because there was no notion of the rank of what was a holomorphic non-commutative manifold at the time. However, the study of differential graded algebras over the quantum flag manifolds has yielded to a better understanding of their non-commutative geometry. And in fact, there were subsequent works on the Borel-Weil theorem for quantum groups that were in fact using a differential structure, even more, a complex structure on a differential star calculus. This was started first by Beggs and Majid that proved Borel-Weil theorem for the foundational example of the Podre sphere. Then Calcali, Landi, Van Suilecom, and Motaderro, introduced the notion of holomorphic vector bundles and extended the proof of Borel-Weil to all quantum projective spaces. And the same notions also appeared in the work of Beggs and Majid on non-commutative coherent sheaves. So as we see, this work on this number of works on non-commutative version of the Borel-Weil theorem proceeded step by step. And finally, let me mention that myself, together with Colin Morodziński, Raymond Bochal, proved Borel-Weil theorem for the quantum Grassmannian. So another small step after the projective complex spaces. And we were using a quasi-triangular presentation of the differential calculus. Now, in principle, this approach is probably possible also for the other irreducible quantum flag manifold. The Grassmannian is an example of irreducible flag manifolds, but it's not doable. We have to take another route to prove the Borel-Weil theorem for these other guys. So let me say let me state the theorem. For any irreducible quantum Flagg manifolds, so this is irreducible quantum Flagg manifolds are of course a subclass of quantum Flagg manifolds. We have that the space of holomorphic sections over a lab bundle EK is an irreducible UQG model of highest weight K var Px. So X here is the cross node of the corresponding to the irreducible quantum Flagg manifold. No worry if you don't get what I'm saying right now. I will, of course, explain everything in detail very soon. So yeah, this is Borel-Weil theorem. And as you see, we can give a concrete geometric realization of the representations of the quantum group of the Lie group, of the quantum group of OQG. Yeah, as I said, we need to introduce some preliminary material in order to understand the statement of this theorem and how to prove it. So I am pretty sure that everybody here knows what a quantum group is. And what, in particular, what Drinfeld-Jimpo quantized enveloping algebra is. But let me remind you, nevertheless, that if we have a finite dimensional complex semi-Lie algebra G of rank L, we can give a non-commutative deformation of its enveloping algebra, associative enveloping algebra. So if we fix a Cartan subalgebra H and we choose a set of simple roots, we have corresponding to it a Cartan matrix of G. And the deformation, the non-commutative deformation of the enveloping algebra is given by this set of commutation relations and the quantum cell relations that I omitted because there's just so much space on a slide. And as you see here, the message, I guess, is that the non-commutativity of these guys depends highly on the Lie theoretic nature of our object. As a matter of fact, and as everybody knows again, UQ of G has the structure of an Hopf algebra. Now, Crash, let me remind you quickly. Let me remind you quickly about the representation theory of UQ of G. So
there is a question in the chat.
Yes.
Okay.
What is QI?
What is QI? Yes. Okay, QI is, so we have the parameter Q, and QI, if we call alpha I the ith simple root, QI is what? QI is Q to the scalar product, the Killing product of alpha I by itself, I think divided by 2.
Can you write it?
I guess, I don't know. I don't know how to write. Sorry.
Okay, forget it, yes.
Okay.
But then say it again. So QI is equal to what?
QI is Q to the power of alpha I by alpha I. I mean, scalar product of alpha I by alpha I. Alpha are the simple roots.
Okay.
So, doesn't like the actual value doesn't matter. The important message here is that you can find the value of QI and the value of every constant involved in these relations by looking at the Cartan matrix of the Lie algebra. Okay, so the Cartan matrix encodes everything here. I hope this was enough because I don't remember this. Yeah, I think QI was Q to the alpha I alpha. Is it fine? Can I proceed?
Yeah, go ahead, fine.
Ah, okay, thank you.
Thank you so much.
No worries. Now, for any UQ of G mod, we have a way to classify all the modules over UQ of G, finite dimensional ones at least. For any UQ G module V, we say that the vector V is called the weight vector, and we denote the weight in this way. If by applying K to V, we know that V is an eigenvalue of Ki of eigenvalue Q to the alpha I scalar product with the weight of V times V. So the weight of V is a tuple of yes, is a vector in R to the rank of in Z to the rank of the Lie algebra. And in the following, this is just a notation. For each lambda, we denote as P plus the span of the fundamentals weights of UQ of G. And there exists, for each one of them, there exists a finite dimensional UQ of G module V lambda, which is uniquely defined by the existence of a weight vector, which we call the highest weight vector, such that EI applied to this highest weight vector gives 0. So,
Alessandro, just a stupid question. When you write Q to this power, you have what? A parenthesis, alpha I, comma, weight, but these are just numbers. So what do you mean by?
These are just numbers, yes.
So what is a number, comma, number?
Ah, sorry, no, sorry. Alpha I, the fundamental roots are vectors, and weight V is a vector. Sorry, I didn't specify this. Like weight of these things.
Is in P.
What?
Weight of V is in P.
Is in P, yes. And P, yes. P is basically, how do you say that? P is a lattice inside the R to the, is in the Z span.
Okay.
Is in, okay, how do we, well, P is basically in Z, is basically Z to the power R, where R is the rank of G.
Okay. Yeah, thank you.
Okay. So yeah, we call any finite direct sum of this representation of UQ of G a type 1 representation. And as a matter of fact, they coincide with the classical representation, the classical finite dimensional representation. And so we know that each type 1 module V lambda will decompose as a sum of weight spaces, which is just to say subspaces of V lambda which are spanned by vector of a given weight. So these are the objects, the representation. This is the representation theory, or I should say important part of the representation theory of UQG. And these are the objects that we're going to realize as geometric objects when we give the non-commutative generalization of Borel-Weil. So this was to show how to give the quantization of a universal enveloping algebra or Lie algebra. And now we can build in a dual manner the quantization of the coordinate algebra of the corresponding Lie group. So if V is an UQG module, a left module over UQG, then of course also the dual module is also V star, the dual of V is an UQG module. And we can consider this function. So this is a function a functional, I should say, from UQ of G into C that takes an element of X and apply X to V, since V is inside a UQ of G module. I get something into V again, and then evaluate an element of the dual on it. So I get a complex number, of course. Then I define the coordinate ring as the subspaces over C of the span of these objects. And this guy is, of course, by construction, is contained inside the linear dual of UQ of G. In fact, it is contained into, sorry, it is contained inside the Hopf dual of UQ of G. So the smallest of algebra contained inside, the largest of algebra contains inside of the linear dual of UQ of G. And an Hopf subalgebra of this guy is given by the direct sum over the weights inside the positive integer span of the fundamental weights of all the coordinate rings. And these objects is a name, we call this guy OQ of G, or the quantum coordinate algebra of G, where G, as I said before, is the compact, simply connected, simply group, having G as its complexified Lie algebra. Of course, if you think in particular to UQ of G to be UQ of SL2 and OQ of G to be quantum SU2, then you get back all the well-known construction of Aronovitz of quantum SU2. And in fact, the general consensus about this pair of objects, the quantum enveloping algebra and the quantum coordinate function of the group, is that they describe a good Q deformation of the classical topology of each Lie group. In particular, they all admit a system algebraic completion as example of Voronovich's compact quantum group. And for Q, let me just end by saying that for Q that goes to 1, OQG recovers perfectly the coordinate algebra of the Lie group G, while the situation is a bit more nuanced for UQ of G, because what I get instead for Q that goes to 1 is some, I think, R-fold cover of the quantum of the classical enveloping algebra. Well, this holds from the topological point of view. The situation, as we know, is a bit more controversial, to say at least from the point of view of differential non-commutative geometry. In fact, there is not known construction of the spectral triples for OQ of G. Of course, we want a spectral triple over the coordinate algebra of the group. There is no known construction of spectral triples of such kind, even for the simplest case that is OQ of SU2. So this happens because if we follow Voronovich's idea to look at Q-deformed geometry starting from the round complex, as we shall see in a moment, we fail for the case of the quantum group of QG. And I guess this is a moment to ask if there is any question.
I don't see any questions yet.
Okay.
Oh, Adam, you have a question?
Yes, maybe just a simple question.
Or semi-simple.
Yes, yes, should be different from 0 and -1 also, yes?
Yes, thank you. Q should be different from 0 and -1.
And 1,
yes? Sorry? And okay, 1 is the classical case. So yeah, you want Q to be different from 0, -1, and 1 for everything to work out. Like this case become incredibly degenerate, you're right. And in fact, you could in principle take Q to be a complex number. I think what you lose here is the star structure on these guys. Not sure though. But even in this case, you want Q to be not a root of unity.
Okay, I'm asking since I'm aware that there is a construction of SUQ2 for Q equal to 0.
Oh, okay.
There are some degeneracy problems.
Wait, Adam, but then coproduct doesn't exist. It's all right as a C-star algebra, it's a graph C-star algebra, but I don't think you really have a compact quantum group. I mean, the coproduct does not exist.
No longer have a quantum group. Okay. Okay. Thank you.
Yeah, thanks, Piotr. Okay, thank you for the question. Shall I go on?
Yes, of course, please.
Okay.
I'm happy, yes.
Okay, so now let me give a brief review of the theory of differential calculi for non-commutative star algebras and their covariant functions for quantum groups. So remember that the differential calculus is given by a pair of a differential graded algebra, which is generated in degree 0. That means that we want it to be generated by elements inside of omega 0 and by their differential. And by, as I just said, by an element D, by an operator D of degree +1, which is called the differential, and whole square is 0, of course. Then we say that for a given algebra B, we say that we have a differential calculus over B if we have a differential calculus such that omega 0 is equal to, is isomorphic to B. And now we will mostly deal with first order differential calculi. That is, we just need the first two guys, omega 0 and omega 1. So let me define a first order differential calculus over an algebra B as a pair omega 1 of D, where omega 1 is a B bimodule, and D from B into omega 1 is a derivation such that omega 1 is generated as left bimodule by elements of the form dB. Then we call the exterior derivative, as we do for the differential calculus case. And let me just remind you that the first order differential calculus always admits an extension as a differential calculus in a suitable sense that you can guess. Now for these objects, we can give also the notion of complex structure, which is a notion that abstracts the properties of the round complex of a classical complex manifold. So a complex structure is not other than a refinement of the graded structure of a differential star calculus. That is, if I have a differential calculus, I look at the z squared algebra grading over omega, such that I have, of course, this first compatibility between the differential calculus structure and the Z2 grading. So K forms are given by AB forms, AB complex forms such that A plus B is equal to K. I have this obvious compatibility between the star structure and the Z2 grading. And finally, I require that when I apply the differential to omega of AB, I land inside the direct sum of A plus 1B and AB plus 1. Of course, D in principle is just an operator of degree plus 1. So in theory, I could land inside, I don't know, A plus 2B minus 1 or whatever. But no, I require that I strictly land inside the direct sum of these two guys. And in this case, I say that I have a complex structure over the differential star calculus omega. And as we do in classical geometry, we call an element of omega AB an AB form. And we denoted by del and del bar respectively the projection of the exterior derivative over the first component and the projection over the second component. As a matter of fact, these del and del bar are star maps. They satisfy the graded Leibniz rule. And even though I didn't write it, they are nilpotent, the square and the partial and overline del and del bar square are both equal to 0. I blanked out for a moment, and they anti-commute. So we have a double complex, a double chain complex.
Sorry, may I ask you a question? Can I have a question?
Yes, please.
Is it automatic that del bar squared is equal to 0 if you assume that d squared is equal to 0 and the composition number 3?
Yes, it follows. Okay, maybe I wasn't clear. This follows from this definition, yes. From the square equal to 0 and from the condition number 3, exactly. Okay. It follows automatically, yes. It's not a further request. Can I go on?
Thank you.
Thank you. So, as I said, I want to give the covariant version. And we say that the differential calculus over is left UQG covariance if omega, of course, admits a UQG left module structure, and the differential is an UQG module map. And we define similarly right covariance and B covariance. And also we say that the complex structure over the calculus omega is covariant if this Z square decomposition is a decomposition of left UQG modules. Well, good. Now the most natural step would be to say, okay, I have my candidates for a quantum deformation of the coordinate algebra of Lie group. I have my definition of a complex structure, and I know that I should have some complex structure in the non-commutative case because I know that there is one in the classical case. But as a matter of fact, and of course we want this structure to be bicovariant and of classical dimension to be called a legitimate deformation. And as you see, as a matter of fact, there exists no bicovariant differential calculus over the quantum coordinate ring of a Lie group, the non-commutative, the quantum coordinate ring of a Lie group. However,
sorry, once again, what does it mean, classical dimension?
Classical dimension, I have a complex structure for Q equal to 1, which is the classical case. And I would like the dimension of omega to be the same also in the quantum case, but this doesn't happen.
So non-classical means that these two dimensions do not coincide, yes?
Well,
yes.
I mean, Adam, think about it as a Lie group. G is a Lie group, so it's a manifold. So it's the RAM cohomology has its dimensions, right? I mean,
right.
I see. Okay.
Right. Thank you.
This is a motivation.
What I forgot to mention is that in the classical case, these informations of the complex structure are enough to reconstruct the holomorphic atlas of the Lie group. So it's in fact enough. It gives me an information about all the needed information about the Lie group as complex manifold. And now, if I look at the dimension in the class of all the differential calculi that I have for the quantum versions, they do not coincide. So they are not. They cannot see as deformations of the classical Lie group in this sense.
Maybe one more question, since this is a non-existent statement. So you claim that there are some G for which there is no bivariant differential calculus with such properties, or it is for every G, in fact?
Good question.
Always a problem, or there could be a problem?
What?
So it is always a problem for every G, or is it a problem?
This is a good question. Maybe I overstated here. For sure, this does not work for OQ of SU2, which is the most basic.
Okay. Okay.
Honestly, I don't know if people then tried to look to differential calculus for other G, but for what I understand, people kind of lost their faith.
I see. So the first test example for this first test example, the answer is negative. So
exactly,
one couldn't hope that there will be a better situation for more complicated G.
Exactly. That's a good point. Yeah, it's true. That's what I know about the literature. People try to for OQ of SU2 and it didn't work. Yeah.
I have a further question, if I may.
Please.
What if you do not assume that the dimension has to be classical? Does there always exist a differential calculus for any G or
OQ of SU2? There exists a bicovariant calculus of non-classical dimension. Yes.
And what about other Gs?
What about other Gs? Honestly, I don't know. I think that there should exist a bicovariant calculi of non-classical dimension for, I think, all OQ of SUN. They have been found, at least.
Okay, thank you.
No worries. Other questions? Okay, so I shall go on.
So, wait, there is a comment for SUN, I mean, probably SUQN. There exists an old paper by Karo Watamura.
Ah, okay, here you go. Okay, thank you. Okay, so let me proceed. So as this problem put on hold like the study of non-commutative differential geometry for quantum groups for quite a while. But then during the year 2000s, people found out that the situation is way nicer if we don't look at the group, but instead we decide to study a particular class of homogeneous spaces of the quantum group G. What do I mean by homogeneous space of a quantum group? So if A is an off algebra, we say that the left coideal algebra of A, let's call it B, is a quantum homogeneous space if, first of all, A is faithfully flat as a right B module, which is to say tensoring by A tensor, tensoring as a B module by A tensor, by A, we send short exact sequences of B module into short exact sequence and vice versa.
Yes.
And moreover, we require that B plus A is equal to AB plus. I didn't write anywhere what B plus is, sorry, but B plus is not other than the intersection of B with the kernel of the counit of A.
Maybe I will just add, because it's an important notion, this faithful flatness, because vice versa is not quite clear what you mean by vice versa. It simply means that if you have a short sequence, when it is exact, if and only if it is exact after the tensor. So one way it's flatness, but the other way around is when it's both ways, it's faithful flatness. So, so sequence is exact, short sequence exact, if and only if it is exact after tensoring. So if you have an exact sequence after tensoring, then the sequence which you tensored with is also exact.
Yes, thank you, Piotr. Yes, exactly. Thank you, Piotr.
Welcome.
Then if all this happens, we have a coaction of PB of A, where PB is the quotient of A over B plus times A, which is given like this. So I take the coproduct of in A and I apply pi B to the second leg of the coproduct. And what happens is that the space of coinvariance with respect to this coaction is given by the quantum homogeneous space. So let's see a class, the class of homogeneous quantum spaces we are interested in, which are the quantum Flach manifolds, as usual. So if this is a subset of simple roots, we can consider the sub-algebra of the quantum enveloping algebra of G, which is given by this guy. So I keep all the elements inside the Cartan subalgebra, all the Ki, and I, now I should be careful, I remove all the EI and Fi, which are outside of the subset of simple roots. Now, this UQ of LS is an opt subalgebra of UQ of G by construction. And I can look at the coideal subalgebra of OQ of G, since UQ of LS of UQ of G has an action on its opt dual OQ of G. UQLS has an action on OQ of G, and I can look at the UQLS invariance. And this guy of QGLS, I will call the quantum Flach manifolds associated to S. Yes, as I forgot to say that from the constant semi-simplicity of UQLS, it follows that OQGLS is a quantum homogeneous space, which, as I said, we call the quantum Flach manifolds associated to S. Now, as I said before, you can define a quantum Flach manifold by taking out a certain numbers of simple roots inside the Lie algebra. And there is a nice picture to think of this in terms of Dynkin diagrams. So for each lead, remember that all the information of an Lie algebra is in some way encoded inside their Dynkin diagram. And we can construct a quantum Flach manifold just by crossing out a certain number of nodes of a given Dynkin diagram. So here, for example, I could, we cross out these nodes and we consider the simple roots EI, Fi corresponding to the nodes that are crossed out as removed. And we look for the invariance with respect to the algebra UQLS that we have defined in this way. And as I said at the beginning of the talk, we are not interested, or well, we will be interested, but we could so far deal only with irreducible quantum Flach manifolds. And this all the reducible quantum Flach manifolds, you see them listed in this table, and they are all Flach manifolds that can be defined, that are defined by removing only one cross node inside the Dynkin diagram. Crossing only one node inside the Dynkin diagram. And this is the picture for the series AN. Here, you can cross any single node inside the Dynkin diagram. And what the quantum Flach manifold that you get is the is a Grassmannian. In particular, if you cross the first node or the last node, you get a projective complex space. Then the other irreducible quantum Flam manifolds are the ones listed in the table for the series Bn, Cn, and Dn, and we also have some flag manifolds for the exceptional E6 and E7. And I should mention also that the irreducible quantum Flam manifolds are also corresponds to the quantum Flam manifolds that are also quantum symmetric spaces with respect to an involution on UQ of G. So they can be characterized in this more abstract way. Okay, why are we interested in this class of quantum flag manifolds? Well, because we can work with them. Why? Because of this remarkable result of Eckenberg and Kolb. For each quantum flag irreducible quantum Flam manifolds, or that is also a quantum Flam manifold of Hermitian symmetric type, there exists a unique right covariant differential calculus of classical dimension. This differential calculus exhibits all the properties that you might want. It exhibits a complex structure. You can build a Hodge map. You can even give a non-commutative Kähler structure to it. And it is a complex structure. So we have what we legitimately call the holomorphic and anti-holomorphic parts of the calculus. Good, so we have something we can work with, because remember we want to look at holomorphic sections for a quantum flag manifold in the end to state the Borel-Weil theorem. So let me remind you that for a first order differential calculus and a left B module F, a connection on F is a linear map with respect to this sort of Leibniz rule. And in the following, we will also need the definition of a line module. Sometimes I will call it line bundle over B, which is an invertible B by module, or that means that there exists another B by module E dual, such that E tensored over B by E dual and E dual tensored over B by E is isomorphic to B.
Sorry, Alessandro, can you go? Yeah, I have a problem with this.
Yes. Oh, that's just me not. Yeah, sorry. I guess I copy paste and didn't make the right correction.
Okay. So this should go out, right?
Yes.
Okay.
A line module over B.
The module over B, so there is a two appearance of B, but
yeah.
these are different.
Yes.
There is one capital B as well.
Yes.
So
yes. There is some
yeah, I guess you can put it like that.
Okay.
Yeah.
DB by module.
Sorry for the typo. Can I go on?
Yes, of course. Yes. Okay. Yes. Go ahead.
Well, now we can define an holomorphic, non-commutative holomorphic vector bundle, which is characterized by classical Cazul-Magrange for holomorphic vector bundles. Sorry, what I wanted to say is that we will look at a pair given by a vector bundle and an holomorphic connection as an holomorphic vector bundle. And no, sorry, not any, but we also have to require that the connection is flat. So remember that we can extend any connection to a map. So a connection is defined on a first order differential calculus, but we extend the first order differential calculus to a complete differential calculus, and we can extend the connection to a map on the differential calculus times the module. which respects this Leibniz rule, the graded Leibniz rule. And the curvature is just the square of a connection. And we say that a connection is flat if nabla square is equal to 0. Then for an algebra B, a holomorphic vector bundle is just a pair of a finitely generated projective B module and an holomorphic connection, which is moreover flat. And we call this the holomorphic structure for F nabla F.
Sorry, may I ask you a question?
Yes, please.
Could you come back to the previous page? No.
Oh, okay.
To this one. Don't you assume that omega 0 p, let's say, or omega 0 comma bullet is generated by omega 0 1?
Omega 0 bullet is generated by omega 0 1, and this follows from the fact that omega is a differential calculus, so it's generated in degree 0. And so all the objects inside of omega 1 are generated by objects of the form dB. And the fact that d of omega AB is contained inside of omega A plus 1B direct sum with omega A B plus 1. What I'm saying is that if you assume that these two conditions, it follows.
Yeah, but is this delta bar a derivation of, is there a multiplication? How do you extend del bar to higher?
Okay, I see. Okay. So del bar is the derivation. Yes, del bar is extended. Is the projection of delta on the component or the component 0 bullet, and it is a derivation once you extend.
Okay.
Yeah.
Thank you.
Boris?
Okay, just one quick question. So this is a definition of a general holomorphic vector bundle, but you assume somehow that this flat zero is that this 0-1 connection is flat.
I assume that is flat, yes.
So this is more like a flat holomorphic vector bundle, yes?
Thing is that I don't know if there is a Koszul-Lagrange theorem. Like classically, the Koszul-Lagrange theorem, which is, you can think of it as the Ceres-1 theorem holomorphic version, works for flat connections. I don't know if it works in full general.
Sorry, this is probably some misunderstanding. So this flat 0-1 connection is not a flat connection.
It's not a flat connection, no. It's flat, or the restriction of 0-1.
So it's an because so one thing is missing here, namely the extension of this del bar to the product omega 0 bullet tensor F to omega 0 bullet tensor with F. And this must be a complex.
Yeah, right.
Yeah, but classically there is a condition for this curvature for being of the type 2-0 or something like this. You don't have this condition for this connection here.
Okay.
Honestly, the vanishing of a 2-0 part of the, or 2-0 and omega, yeah.
Okay, I see. Honestly, I don't know any much better about what are the requirements for Koszul-Lagrange in full generality. So yeah, there might be something missing. I'm sorry.
So this means that simply you have the Dolbeault complex.
Mm-hmm.
Okay, and this is your definition of a holomorphic structure.
Yes.
Okay, thank you.
Mm-hmm.
Yes,
Okay.
this is my definition.
So this flatness refers only to this del bar, not to the whole connection.
Not
yes?
to the whole connection. Yes.
Okay. Thank you.
Okay, so now we are going to build a bunch of this of B left model with an holomorphic connection, which are going to be given by line bundles over the quantum Flam manifold. How we do it? We have to introduce another object, which is the quantum Poisson homogeneous space. So remember that the Levy subalgebra LS classically is reductive, and it decomposes into a semi-simple part plus a U plus an abelian part. Sorry, a commutative part. Then we, from the quantum point of view, we are motivated to consider this Hopf algebra. So remember when I was defining UQ of LS, the quantum the quantum enveloping of the Levy subalgebra corresponding to S, I was removing only the simple roots EI and FI corresponding to the non-crossed nodes inside the linking diagram. And now I remove also the KI corresponding to the non-crossed nodes. In this way, I obtain a smaller algebra contained inside of UQ of LS. And I can consider again the coideal subalgebra, of invariance, which I denote in this way, and is known as the quantum Poisson homogeneous space. The quantum Poisson homogeneous space associated to the subset of simple roots S. Okay, yeah, what about?
I have a problem with this definition. We call OQ the quantum homogeneous Poisson space associated to S. So what's the origin of the name Poisson here?
Honestly, this is not my definition. I don't. This was the name that was given in the original paper where these guys were introduced, which was a paper. I don't remember the name of the authors. I'm sorry, but this was the name that was given in the original paper where these guys were introduced. My guess is that in the classical case, these spaces are in fact Poisson spaces. I don't know if this helps in any way, but for the Grassmannian, for example, if you make this construction for the Grassmannians, the space that you get are the Grassmannian spheres. So yeah, I don't know why the authors that defined these objects decided to call it Poisson space.
Okay.
I can send you some material later if you want, by the way.
Oh, there is an answer on chat to this.
Oh, okay. I'm sorry. Okay, good.
Okay.
Can I see the chat? Because I'm... Oh, can I see the chat? Oh, jeez. So.
So the answer was...
this is to distinguish from the coisotropic case. Okay.
Yeah, makes sense.
I guess it makes sense, yes. Thank you, Tomasz. Any more questions? Okay, let me proceed. Now, some notation, because I want to give another construction of these objects in terms of direct sum of line bundles over the quantum Flam manifold. So remember that for an irreducible quantum Flam manifold, we have only one simple root, which is not contained in S. And we denote by VI, I goes from 1 to n, the weight basis for the corresponding for the UQ of LS module V pi Vx, the one such that Vn is the highest weight vector. So now we denote by the dual base, and n here is the rank of the Lie algebra, of course. Now we denote, if we denote the dual base by Fi, we can give a set of generators of the quantum Poisson homogeneous space in this way. So remember, these are the quantum coordinate functions. And we denote by Zi and Zj, these two objects, where here n is the here n is the dimension of V pi of x. Then for then this is a set of generator of OQ of GLS. And I can give another construction of Q of GLS. Let's start by defining inside of OQ of G the homogeneous coordinate ring SQ of G over LS, which is the subalgebra generated by the element Zi introduced previously. We define also the opposite homogeneous coordinate ring as the subalgebra generated by the element Z bar I. Then both these guys, as a matter of fact, are quadratic algebra, and then they inherit from they inherit the natural Z grading, which is just given by counting the degree of the monomials into Zi and Z bar I respectively. It turns out that OQG, that the quantum Poisson homogeneous space can be described as the quotient of this tensor product by a certain central element of degree 0. Hence, again, the grading, the sense to a Z grading over the Poisson homogeneous spaces, and we have that the degree of Zi is equal to 1, and the degree of bar Zi is equal to -1. Okay, big deal. We have this construction of the Poisson homogeneous spaces as a quadratic algebra. What should we do with it? Well, we have a direct sum decomposition of OQGL of the quantum Poisson homogeneous space into simple subobjects. And this decomposition is in fact a decomposition into line bundles, into relative line modules. And this gives to the quantum homogeneous space the structure of a strongly graded Z-graded algebra. Moreover, every relative line bundle over the quantum Flam manifold is isomorphic to one of the guys appearing in this decomposition. So now we know that every line bundle, which are the guys we are ultimately interested in, every line bundle into the quantum Flam manifold is contained as a direct sum into the Poisson homogeneous space.
Sorry, could you explain this word relative?
Yes, relative, well, each line bundle is an object inside the category of left comodule and of left A comodule, where A here is OQ of G, and B bimodule.
Where B is this is B.
Where this, yes, thank you. B is the, no, sorry. B is the, B is yes. OQ of GLS.
Ah, yes, sorry, I didn't, yeah, of course, yes.
Okay. They are OQ of GLS bimodule. And the relative means that there is a certain compatibility between the coaction of OQG and the action of QGLS, which is what allows one to use Takeuchi equivalence in this context. That allows for, okay, I didn't want to mention this, but what we use through all the paper is this Takeuchi equivalence, which is a way to describe objects inside of the category of left OQG comodule of QGLS bimodule as objects. So I have an equivalence between this category and of left OQ of LS modules. Okay? And in order for this equivalence to hold, I have to ask for this compatibility between the coaction of OQG and the action of OQGLS. And I guess that it's just asking if B is an element inside of OQGLS and A is an element inside the line module, then I can compute the coaction, the A coaction, the OQ of G coaction on B times A. And this is equal to the coproduct of B applied to the coaction applied times the coaction applied on A.
Sorry, I would like to check if I understand what's going on. Is this true that these line bundles EI are irreducible, come from irreducible representations of this Cartan part of this decomposition of the this?
They come from irreducible representations, irreducible one-dimensional representations of this OQ of LS, which I didn't introduce, but is the Lie group version of UQ of LS that I introduced before. Okay, so
so this semi-simple part is a part of the composition of a reductive classical of the reductive algebra.
Yes. And
there's a remaining abelian part.
And there is a remaining abelian part, yes.
And eigenspaces of representations of
yes, this HEI is an eigenspace with respect to the to the abelian to the coaction of the abelian part.
Okay.
Yes.
Thank you. Yeah.
Alessandro, could you remind me, please, the relationship between this OQGLS and OQGLSS?
Sure. OQ of GLSS is given. So, I mean, actually, I'm going to talk about this a bit later, but we will find that OQ of GLSS is a quantum principal bundle, gives a quantum principal bundle over OQ of GLS.
So classically, it is like quotient by algebraic torus.
Yes, yes, exactly. Like what you have is a quotient, like OQ GLSS will give a torus bundle over of Q of GLS.
But which is which? Which is with two S's, which is with one S?
Is the total space. And of Q of GLS, you can see inside this decomposition as the part E0. Okay, so it's the base. Okay, so it's the quotient with respect to this. So think maybe the simplest, the simplest case is when of Q of GLS is the Podler sphere. Then in this case, of Q of GLSS is OQ of SU2. As this is the composition of OQ SU2 as line bundles over the Podres.
Of course, yeah, I understand it. And what is OQG in this example?
Of QG and of QGLS in this example coincide. Okay, but this is not the case in all the examples, of course. This is, of course, the Podres sphere is a very unique example because it's an irreducible quantum flag manifold, but it's also a full flag manifold. By full, I mean that all the crosses of the corresponding Dinky diagrams are crossed, okay? When this happens, I am left with a space which is invariant solely with respect to the action of a certain torus. Okay, and this space in fact corresponds with the entire group for OQGLSS. And I got something below which is known as the full flag manifold.
I remember that this OQGLS was defined as some fixed points of algebra. You take OQG and you have some action of some Hov algebra, which is related to this LS.
Yes.
And then the fixed points of algebra is this one. So it's like a homogeneous space. I have this quantum group, and I have a homogeneous space. But you are saying that you can do like an intermediate quotient.
I can do an intermediate quotient, exactly.
Okay.
GLS is an intermediate quotient.
Okay, thank you so much. This is what I want to understand. Thank you, I appreciate it.
Like if you want also, you can think of the fact that from LSS, from the semi-reductive part, I have removed more stuff because I have removed also the commutative part. So I have now a space of invariance with respect to a smaller algebra. That is
I've got you. Yeah, thank you so much. Yes.
Can I go on? Or
go ahead. Go ahead.
So now we want to study the holomorphic sections for relative line modules. And as a matter of fact, we know from a theorem of a bunch of people here in Prague, that's Garcia, Krutov, Obokala, Somberg, and Strung, that for each relative line module, there exists a unique left OQG covariant connection over EK, which is...
Sorry, so this is still 0-1 connection.
0-1 connection, an holomorphic connection, yes, sorry. An anti-holomorphic, yes. So now we know of the existence of this guy. We knew of the existence of this guy. But what we did also was to give a construction of these unique connections as associated to a principal connection. And this, as I was saying before, I didn't close a parenthesis here, sorry, no. This presentation will require to show that the pair given by the homogeneous Poisson space and the differential calculus over the homogeneous Poisson space. I didn't review about this, but basically you have an extension of Eckenberger called calculus that was a calculus over the flag to a calculus over the homogeneous Poisson space. And we will show that this gives a quantum principal bundle. And in general, I mean, as I will recall, to show that something gives a quantum principal bundle can be a non-trivial task. That's why we introduced this object, the principal pairs, to show the quantum principal bundle condition.
Sorry, I have a question about this notion of quantum principal bundle. So this differential calculus is a part of the definition.
It's part of the definition, yes. This is part of the definition that I guess, yes, Brzezinski and Maget gave some years ago. It is how it is, this definition.
Okay. Didn't you miss parentheses here?
I did, Piotr. I'm very sorry.
Because, you know, later I'll ask you to send me corrected slides. That's why I'm
sure.
pedantic.
Sorry for all this typos. So, yes, this is the definition of quantum principal H bundle in its full glory. So, quantum principal H bundle is a pair consisting of a right H comodular algebra P and a right H covariant calculus first order calculus, let's say omega 1p, such that P is an off-Galois extension of the space of its coinvariants with respect to the coaction of H. And I didn't mention it, but every calculus, every first order differential calculus can be presented as the quotient of a universal first order calculus by a certain, by a sub-bimodule n. So we have a first order differential calculus here, and if n is the sub-bimodule of the universal calculus that corresponds to our calculus, we have that this map var of n, which is the composition of the canonical map that defines the off-Galois extension and the projection after the projection of over B, over B, yes. Then no, sorry, projection of B is the projection of, so omega 1p, omega 1 universal P lives inside of P tensor P, and we consider the projection over the balanced tensor product. Then we compose with the canonical map. And if the vertical map, if this var map applied to the sub-bimodule n gives P by I, where I is a some adjunct subcommodule right ideal, then we say that we have a quantum principal H bundle.
So by this n, you mean the kernel of the projection from the universal calculus to
yes,
omega 1 of
n is exactly n is the kernel of the projection from the differential from the universal calculus to our guide, to our differential calculus. Yes.
Okay, thank you.
As you see, proving the quantum principal bundle condition can be quite difficult at times, but we, in our context, which is also, I'm glad that Piotr pointed out that we have this context in which we have an intermediate homogeneous space, because this is exactly the context that we can generalize, and we did. We define a principal pair of quantum homogeneous space BP as a pair of quantum homogeneous space for a certain off algebra, by the way, let's say it's A, such that PB of P is an off algebra. Now, how much time do I have? Okay, I have enough time to say something about this. So,
sorry, what is pi B?
Pi of, yeah, pi of B, remember a quantum homogeneous space, I denote, okay, let's say that these guys are quantum homogeneous A spaces with respect to a certain off algebra A. Then pi B is the quotient from A into A quotiented by B plus A, okay? Is the map that it's the quotient map that defines the quantum homogeneous space B. It's the map that gives me the coaction.
Wait, so you have some Hopf algebra denoted by A.
Yes, that I didn't write. I will correct also this in the, yes.
And P coacts on, and A coacts on P, right?
And they coacts, so how is it? I go from P into, okay, wow. I go from P into what? Into A, no, into P tensor, sorry, P tensor, P tensor A over P plus A, right? Because this is an homogeneous space.
B tensor A?
P
tensor A, that's what I was writing.
P tensor, yes, A over P plus times A, right? This is the,
yes.
This is a P, yes, exactly. Now P plus A.
Yes, of course, yes.
Okay, and of course, same thing for B, right? Because these are quantum homogeneous spaces. That's what defines the coaction of quantum homogeneous space.
Yes.
right?
Or is the fact that P plus A is a Hopf ideal related to the name Poisson in this?
No, this is, or maybe, I don't know.
It is. Tomek, you're right, it is. Because in general, it's just a co-ideal, right ideal.
In general, it's just a right ideal, yes.
Yeah. When it is two-sided, it means it's Poisson.
I have to say that subconsciously, maybe, decided to denote it by P because in our picture is going to be the Poisson homogeneous space. Yes.
Mm-hmm. Yes. And I understand you correctly that P is a subalgebra in the Hopf algebra A.
Yes, P is the space of coinvariance of A with respect to the coaction. Sorry, in general, I have also coaction from A into A tensor A over P plus A, and P is the space of coinvariance with respect to this coaction.
Yeah, okay.
I have the same kind of map for B.
And you have the same, okay, so you also have it for B, right? So B.
Exactly. So let's say, okay, sorry, Piotr, I think something like I have this map, but these two maps I have on the whole A. Right, so I have a map that goes from A to A tensor A quotiented by P plus A, and from B into B tensor A quotiented by B plus A, right?
Yeah, so that's what I'm trying to write.
No, it should go
it should go to A tensor
into.
Why can't you write? I mean, it would be so much more helpful.
Yeah, you're right. I'm not.
So base is a homogeneous space, so this should be left coaction of.
Yes, I have these two maps. One, sorry, control. How do I erase? Okay, you erase here. The thing is that I never try to write, so. Okay, no, I don't want the eraser anymore. I want, draw. Okay, so how do you okay. I have again the situation under control. One, sorry, this is not my computer. So okay.
Yes, now makes sense. Yes, of course.
Yes, sorry. Okay, now I have this coaction.
Yes.
And I have also the coaction, the corresponding thing for B, right?
Mm-hmm.
Right. So I have, let's say, okay.
And now it's B plus A.
This is supposed to be an A. B.
Yeah.
A, right?
Yes. Mm-hmm. Yeah. Yes.
Pi B. Okay. Now P. And
wait, but what's the domain of pi B?
Pi B, the domain of pi B is A, but
okay.
it's contained into A. This is pi P, right? So P is contained into A as the space of coinvariance with respect to this.
Yes, that's classical Schneider.
Okay, so sorry, let's call this guy.
Yeah.
Let's call this guy delta because I want to. Okay, so this is with respect to delta of P, the coinvariance. Now, if I denote by pi B this quotient, I can consider pi B of P, right?
But I'm losing here and say I denote by pi B this quotient. Is pi B a map or a space?
Pi pi b is a map.
Okay, so you cannot call it a quotient. You mean a quotient map?
Quotient map, yes,
Okay.
sorry. Okay, sorry. Sure, I guess, yeah.
Okay.
Quotient map, yeah.
Okay.
Sorry, that's...
Okay, and when you restrict the quotient map, which is from A to A divided by B plus A, you restrict it to P, which is a subalgebra of A.
Yes, exactly.
Okay, yeah, thank you, now I understand.
Okay, sorry. In particular, one can prove which is also, that is also always a sub-coalgebra of A.
Mm-hmm.
What is not trivial, of course, is that the antipode restricts. Okay,
mm-hmm.
So it's actually a requirement that you want pi b of p to be an off-algebra.
Mm-hmm.
So classically, this picture corresponds to fibrations with this picture gives so this picture corresponds classically to this. We have a certain group G, which corresponds to A,
mm-hmm.
and we have two subgroups. Say M and N, which corresponds to B and to P. Okay.
Mm-hmm.
So in particular, okay, B is the smaller. So in particular, let's say that M is the, so in particular, let's say that N is contained into M, okay? So of course, I have that the space corresponding, so I can consider the quotient of G by M and the quotient of G by N. And the space corresponding to the quotient by the smaller group is going to contain the space corresponding to the quotient by the bigger group. And I will always have I will always have a vibration of the bigger, so I will always have a vibration of the bigger space over the smaller space as base, and what is going to be the fiber of this thing? It's going to be M quotiented by N. So the fiber is going to be given by the bigger subgroup of G quotiented by the smaller subgroup of G, right? Now I can ask, is this vibration giving me a principle, is this vibration principal? Like, is M over N a quantum subgroup? Is over, no, not quantum, is over M over N a group? And of course, this is not always the case. I have to require that N is normal inside of M, right?
Yes, yes.
And this in the quantum setting is the exact corresponding to require that the space of given by this quotient pi b of p gives an off algebra. Okay, so in particular, if I remove this condition that pi b of p is that pi b of p is an off algebra, I get, just from this setting, I get a quantum vibration where the fiber is an homogeneous space, according to the definition given by Brzezinski and Szymanski. And if pi b of p is an off algebra, I get back a principal commodule algebra, actually.
But you do assume all the time that P is a Hopf algebra.
No, I don't assume that P is an off algebra, no. In fact, in many cases, it's not. What is an off algebra? Like, consider, so again, the simplest case, okay, in the simplest case, P is actually an off algebra. But in the case in which be, well, like one case, like, okay, the case that we're going to consider is the case given by the pair of a quantum Flamp manifold and a Poisson homogeneous space, and pi b of p is going to be that torus that we mentioned before, okay?
Mm.
I guess more concretely, you can think of B as, I guess you can think of B as quantum CPM, and I think in that case the Poisson homogeneous space is going to be a quantum sphere, and yes, and pi b of p is going to be again a torus, or U1. It's going to be U1, of course, right?
Okay, I think I've got it. So what you really assume is that A divided, let me write, A divided by P plus A is a Hopf algebra.
Yes, yes.
So this means that this is a two-sided ideal. That's the Poisson adjective.
Yes.
And you also assume that A divided by B plus A is a Hopf algebra, right?
Yes. Remember, in my definition of homogeneous space,
yes,
P plus A is equal to A B plus, and also for P of
yeah,
P.
exactly. So
this quotient is an Hopf algebra. Yes.
So these are Hopf algebras, but now you are saying, let's take this map. Well, basically, you can say the following. It makes perfect sense. Instead of some pi b, you can just simply say P divided by B plus A. It makes perfect sense, no?
Yes, yes. This is this map. Yes, the map is that the quotient map corresponding to this quotient.
Or maybe I should say B plus P, whatever. I don't know. I'm not sure.
Yes, yeah. I guess it should be the same, right? It should give, but B plus P. Yes. Otherwise, it wouldn't make sense. Yes.
Yeah. Okay. Okay. I've got you now. Thank you so much.
Okay. So yes, this is a particular case in which the description of in which the realization of a quantum principal bundle can be automatic. In fact, if I have a principal pair and I have a first order differential calculus over P, such that omega 1p is left a covariant and right covariant with respect to the action of the Hopf algebra given by the quotient of A by P plus of A, then it holds that as a result we get that the pair P omega 1 of P is a quantum principal bundle. So I think this is pretty nice. Like we can verify that we realize a quantum principal bundle just by looking at some inclusions of quantum homogeneous spaces and to the covariance of the differential calculus.
Sorry, Alessandro, just a small remark. You have -3 minutes to finish your talk, and I see 26 out of 34, which is pretty scary.
Okay, thank you. So maybe I can run a bit. Why are we interested? Well, as we anticipated before, the pair given by a quantum Flamp manifold and a Poisson homogeneous space is a principal pair. And the pair given by the Poisson, in this way, using the proposition before, we proved that the pair given by the Poisson homogeneous space and the antiomorphic first order calculus over the Poisson homogeneous space gives a quantum principal bundle. Now, remember that if I can define a principal connection for a quantum principal bundle as a projection from omega 1p into omega 1p such that its kernel corresponds to what we call the horizontal forms, which are elements inside p omega 1b p. And the principal connection pi is from, sorry, Piotr, I didn't mention that the definition of strong connections is yours.
Thank you.
And the principal connection is called strong if identity minus pi after d of p is contained inside omega 1b times p multiplied only on the right.
Yes, exactly.
Now, if we have a strong connection, a strong principal connection over a quantum principal bundle, we can build associated connections on the right subcommodule.
That's exactly how I came up with this condition. I needed to have this connection.
How do we do it? We remember that we have a multiplication, an isomorphism given by the multiplication map from omega 1b tensor over b e into omega 1b e, and the strong principal connections defines a connection in this way. Now, what we proved for our specific case is that the zero map on omega 01, forget about this whore, I will correct this as well, is a left OQG covariant strong principal connection. And hence we can we can build our unique holomorphic structure, our unique holomorphic connection over EK, just as the connections associated to the zero map. Now we have all the needed ingredients to prove the Borel-Weil theorem. So we have the flag manifolds that I defined for you. We have the line bundles of over the flag manifolds, which are given as which are the direct summands of the Poisson homogeneous space. We have a connection that we have built from the principal connection. So we can prove the statement of the Borel-Weil theorem, except that you should worry about the one with the proof that since once we have all the ingredients, there is just some algebraic manipulations to perform. Let me just point out one important middle step between the proof for the proof. So that is the what I think we legitimately called Liouville theorem for the irreducible quantum flag manifolds. So for any irreducible quantum flag manifolds, we can look at the space of holomorphic sections from of QG LS into omega 01 GLS. And this space turns out to be given just by C. Otherwise, if we state this in the classical context, of course, we see that this is Liouville theorem, because what we see here is that the only holomorphic sections over a flag manifolds are given by constant functions. Then, holomorphic sections inside the differential from the base given by the flag manifold into the differential calculus. Then we use this to prove the statement of the Borel-Weil theorem that now I can show you in all its now we can understand all the objects in this statement. For any reducible quantum flag manifolds of QHLS, we see that the holomorphic sections over the line bundle give an irreducible UQG module of highest weight K var P of X, where P of X is again corresponds against the representation given by the simple root alpha X that was the one crossed out to define the reducible quantum flag manifold. And we can we have given a geometric construction of all these guys, and we're happy with it. So I guess I just have to thank you now for your attention.
Thank you very much. Okay, where is my symbol of clapping hands? Okay, are there any further questions? I see only clapping hands. I don't see any raised hands.
There is
Adam Vegert, raised hand. Okay, Adam.
Yes, I have a very general question, and in fact, I've asked this question several times, but still I'm not somehow satisfied. And the question is the following: that there is the whole theory of spectral triples, which is, okay, very nice axiomatic approach to non-commutative geometry. And there are also many examples coming from, as you explained, from quantum groups. There is some kind of deformations. And as you said, there is a problem for defining a spectral triple, the structure of a spectral triple on all these examples. And I don't know what kind of answer I would be happy with, but I would like to know your perspective, your view on this phenomenon.
Can I ask a comment? Hi.
I mean, I recommend.
Well, I think there is a paper by Sergei Neshveyev and Lars Tusen. They constructed isospectral.
Yes.
Spectral triples on all quantum deformation of simple, semi-simple Lie algebras.
I would be interested.
Okay.
Yes,
I think it's 15 years old, about pre-printed list of 14.
There is this paper, and let me also point out that there are we expect that it will be possible to build spectral triples for all the reducible quantum Flag manifolds. In fact, for all the quantum Flag manifolds. Like for all of them, the greatest difficulty is that we are still defining calculi for the remaining guys. There are spectral triples for, people define spectral triple for, well, Ludwig and Francesco defined the spectral triple for CPN, if I remember well. And then people define the spectral triple also for, let me show you. So let's go back to the table of irreducible quantum Flag manifolds, shall we?
Mm-hmm.
Okay, so spectral triples have been defined for all the CPN, then Obuakala and Diaz Garcia Welmer defined it for the Flag manifold over B2. And I think that Obuakala and with Raymond and Freddy are working also for the quantum Flag manifold over C2. Well, a project that is making me smashing my head against the wall is to define a spectral triple for quantum Grassmannians. So, and it seems doable even if many computations are involved. So the difficult part here is always to prove that the resolvent of the Dirac operator is compact, right? The strategy here is always to try to find some per tesserati formula in order to prove that compactness of the Dirac operator. Now, this means that we have legitimate spectral triples on the homogeneous spaces of the group. We hope that this will somehow tell us how to define a spectral triple starting from these geometric elements also for the group itself. Okay?
So it is expected to hold, yes?
It is expected to hold. It is expected.
Okay.
I could bet whatever you want that it will hold for this quantum homogeneous space. Like, I have no problems. A more risky bet would be to say, okay, I have the spectral triples for the homogeneous spaces. Am I going to be able to lift them to spectral triples to the whole group in some way?
Mm-hmm.
I have faith, but this is a leap of faith from my side, that this is possible in principle, even though this might require to do something funny like twisting the differential calculus or something like that. Twisting the definition of differential calculus or something like that. So yes, if you ask me, like, because from a moral point of view, like, these spaces are all these homogeneous spaces are always invariant with respect to the action of the Cartan part of the Lie algebra. So what you have to add from passing from the homogeneous space to the group is this action. And you have to find a way to do this in a coherent way, in a nice way, such that you, I beg for your pardon, but don't fuck up when passing from the homogeneous space to the group. And it's probably telling us that we should look at some slightly modified version of differential calculus. I hope it was a satisfying answer somehow.
Yes, very optimistic. Since I was always maybe convinced it's too much to say, but I had the impression that these two approaches are have very little in common. And now I'm more optimistic. So thank you.
Can I comment, please?
Go ahead, Tom.
May I comment on exactly the same thing then? Because first I want to take a bit off the optimism. Thomas, is this okay if I comment on it?
Yeah, go first, Elmar. Show yourself.
Yes, please.
Because the first thing is, Heckenberger and Kolb have the Dirac operator in the paper for all these irreducible flag manifolds. It's written in Istvan and Stefan's paper on BGG resolution. You just dualize, you get a Dirac operator. Still, it's difficult to prove it has a compact resolvent.
Yes.
And the problem is the Barasati formula works for the spin manifold. These are the Dirac operator on a Dobold complex, which works for the irreducible. Now, as much as I understand, well, for this irreducible flag manifolds, this BGG resolution gives an elliptic operator. If you take unreducible flag manifolds, you get a parabolic operator, it will not hold a spectral triple. So your optimism that you have for your groups of your other irreducible flag manifolds, I would give you a warning. I don't expect them to give this Dobold operator doesn't give you a spectral triple. Only for the irreducible ones, you don't have to look for the formulas. It's written in Heckenberger-Kolb's paper.
Okay, thank you. Also, Elmar, thank you, and also I'm happy that we finally met, even though in virtual formula I was,
1 hour late because of the time shift. I'm sorry.
Yeah, no worries. Thank you. Anyway, okay, maybe I'm too naive to be so optimistic. I don't know.
I can tell you why you are too optimistic as well, because you don't deform the classical torus. You get, if you mod out the whole torus, you are left with tension space. If you know the Heckenberger-Kolb tension space, these act as differential operators. If you leave one element more inside, this one that won't act as a differential operator. And you cannot twist. So you have some differential operators which work twisted, and you have some which work untwisted. And these don't match to an honest spectral triple. You can try, but I'm sorry, I'm not so optimistic. It won't work. I tried for a while.
Okay.
Yeah, you cannot match. That's the reason. It's exactly the reason why Heckenberger-Kolb has the classical dimension, because the tension space has the same dimension. Mm-hmm. Yeah, if you want to have a nice bicovariant differential calculus, as you're suggested with your principal bundle definition, well, bicovariant differential calculus, you will never get a spectral triple. Yeah, these operators, the Casimir is a second order differential operator, but it's the one that defines the bicovariant differential calculus. So I'm not optimistic. So what to say in Nashviev did was the Dirac twist. It's an isospectral spectral triple, but it's not a good differential calculus. It's infinite dimensional. So the only good examples are when you mod out the whole torus and you're left with differential operators. And that's Heckenberger-Kolb. They've voted in their paper.
Okay, so after killing this optimism, do you still want to add something, Tomek?
Yes, I can kill it even more.
Okay.
Because In the classical case, the classical Dirac operator can be given as a del bar plus del bar star for square root of top degree holomorphic differential forms. But identification of the square root of the top dimensional holomorphic differential forms would require to know that at least part of this classical dimension survives. If you cannot guarantee that you have this classical dimension, there is no correspondence between the Dirac and this Dolbeau operator.
Absolutely correct, Tomasz. And you can, in this list, you take out half of them, because even in the quantum case, you can see if you can take the square root of the canonical bundle. If the square root exists, you are fine. You can construct a spin bundle. If it doesn't exist, it's only complex spin.
Yes.
Okay. So now that you have completely killed any optimism, I think if there are no further questions.
I would have one quick question.
Okay,
what about bot version of this theorem? About higher cohomology.
About higher cohomology, yes.
It's hard to remember.
Like the Borel-Weil bot was also proved, not by me, but by, I think the paper was in the, there was, I think the paper was from Diaz Garcia, Krutov, Obokala, Strung, and it should be their paper. I think the title is Holomorphic Vector Bundles something. I don't remember.
Okay, thank you very much.
Okay, so Tomek is happy. Anybody else? Richard? No?
I'm happy.
Okay, so in this case, Alessandro, grazie mille one more time, but please don't go away. Today is a very important date. Today is 30th of March. And can you see my screen?
I can't.
Anna.
Yeah, now I can. Okay.
Now, can you see my screen?
Yes, I can.
Okay. So today is 130th birthday of Stefan Banach.
Okay.
And so if you need a reason to go for a drink, this is a perfect reason to go for a drink today. He was born in Krakow. So some people are in Krakow right now, and I just came from Krakow today. So Adam and Andrzej in Krakow, and this guy was born in Krakow exactly 130 years ago. So please celebrate Stefan Banach.
Happy birthday, Banach. Okay, I don't need a reason to go for a drink, but for sure I can use an excuse.
Yeah. It's always good to have an excuse. Okay, so in this case, let me stop sharing, stop recording. So thank you very much, guys. And next week, it will be Wouter van Zuilenkom speaking about his joint work with Alan Kohn. So see you next week. Thank you, Alessandro.
See you.
Grazie mille.
Thank
Ciao.
you.
Ci vediamo.
Grazie.